Okay, we're lagging behind as far as the coverage is concerned. This is the first chemistry concept of Chem 252. Whatever after the discussion of chapter 4, alcohol chapter was supposed to be on 251. Okay, so your more responsible for this chapter than alcohol's chapter, but it hasn't been covered in Chem 251, so I had to cover that. At least some important concepts needed to be covered. So today we will be discussing ethers and epoxides, thiols and sulfides. Thiols are synonymous with alcohols. Instead of OH, we have SH. Sulfides are synonymous with ethers. Instead of oxygen, we have sulfur. Okay. So these are the concepts that we'll be focusing on, and these are the objectives that you would be expected to be able to do at the end of the chapter. Okay. So please take a minute and go through those slides. Some of the things I would be rushing. Nomenclature, you don't have to be you don't have to be taught how to name ethers, right? And you would rather want to be taught the chemistry concepts and what you say, the reactions and synthesis of ethers is much more important than nomenclature. But anyhow, there are two ways of naming ethers. Ethers are functionally alkylated derivatives of alcohol. If you have an alcohol, if you do an alkylation, you can make ether. Ethers have oxygen flanked by two alkyl groups. Oxygen is singly bonded, so this can be regarded as dialkyl derivative of water. You take water, and if you do two alkylations on water, both the hydrogens are swapped with alkyl groups, and as a result you can make ethers, right? That's not how we make, but you can regard this as substituted water, disubstituted water, right? Oxygen is sp3 hybridized carbon. There are two lone pairs, and these are called sulfides. Notice that oxygen is replaced by sulfur. Sulfur is in the same group as oxygen, the same valency. All the bonding, all the structural features of ethers are still valid on sulfur. Sulfur has two pairs of electrons. Only difference between oxygen and sulfur is that oxygen only has up to p orbitals. Sulfur has access for d orbitals. As a result, you can expand the valency of sulfur. Sulfur can make 4 bonds, 6 bonds, 8 bonds, depending upon the oxidation level. But carbon can only make 4 bonds, and so is oxygen. It can only make 2 bonds, right? Because they don't have p orbitals. Alkyl groups could be symmetrical. We call these as symmetrical ethers, or they could be asymmetrical. One could be phenyl, one could be alkyl group, one could be ethyl, one could be propyl. Then you have to be naming them differently. These are called cyclic ethers. This is called tetrahydrofuran because furan is aromatic derivative, and if you hydrogenate furan, you get tetrahydrofuran. If you supply 2 molecules of hydrogen to tetrahydrofuran, that becomes hydrogenated. All the double bonds are gone, and you get saturated cyclic ether, and this is called furan. Furan is a common name for a heterocycle. So that's where the name is derived for this. This is commonly used in organic synthesis. That's called THF, tetrahydrofuran, right? And that's an epoxide, 3-membered containing oxygen ring. The structures are not very visible, but as you go further, I think they're much more clear. And again, the sulfides can be symmetrical sulfides. This is diethyl sulfide, this is diethyl ether, and this is again phenyl methyl sulfide. So just replace ether for a sulfide when you see sulfur. This is tetrahydrothiophene. Nomenclature, again there is a common way of naming them. You just find out the alkyl groups, methyl, ethyl, but just alphabetize it. Ethyl comes before methyl, so ethyl, methyl, ether. There is space between ethyl, methyl, and ether, right? And here you have a chloropropyl group on one side, ethyl on the other side. So alphabetize the name. 3, this is where the chlorine is, so it's at the 3rd position. So 3-chloropropyl ethyl ether. This is common common way of naming them. It's not IUPAC nomenclature. This is diethyl ether. When the two alkyl groups are same, you don't have to say it's ethyl ether. Instead of saying ethyl ether, you just use prefix di, right? Diethyl ether, dipropyl ether, that's only valid when you have symmetrical ether. For example, this is diphenyl ether, diisopropyl ether. But if you have two different alkyl groups, you have to find out the alkyl groups and alphabetize the alkyl groups, use a space between the alkyl groups, and then add at the end ether. If it is sulfur, just take off the ether and put the sulfide. Okay. And there is other way of naming these functional groups. That is to use this as a substituent, including the oxygen. You are using that as a substituent. So whatever the longest alkyl group, that becomes your parent chain. So this is my longest alkyl group. So I take this as a substituent. So it's methoxy ethane. Ethane is for the parent chain, and this is regarded as a substituent. And this is IUPAC way of making them. This is ethoxy ethane, right? And if you have a substituent like this, then you start numbering from this end, because oxygen gets a higher preference than chloride. So 1, 2, 3, 3-chloro, 3-ethoxy, and that's my parent hydrocarbon chain, propane. So this whole molecule is regarded as a propane, and the disubstitute as propane. One substituent is ethoxy group, the other substituent is chloro. Which one gets a higher priority when numbering? Oxygen gets a higher priority than chloride. So another way around. Chloride gets a high priority, and this is regarded as a lower priority. So 1-chloro, 3-ethoxy propane. This is sulfide, as I said, methyl sulfide. But if you alphabetize, it is ethyl methyl sulfide. This is diethyl sulfide. Cyclopentenyl methyl sulfide. For naming in IUPAC way, you use this as a substituent. This is your parent hydrocarbon. Methyl thioethane, ethyl thioethane. Thio is for sulfur. Oxy is for oxygen, right? And that is cyclopentenyl methyl thiocyclopentane. Cyclopentane is the parent hydrocarbon, and that is regarded as a substituent. The smallest alkyl group containing sulfur is regarded as a substituent. This is your parent side chain, or parent chain. There are some cyclic ethers. This is called oxidane, oxetane, oxolane. Depending upon the number of atoms in the ring, the terms are little changed. Oxidane, oxetane, that is for 4-member ring. 5-member ring is called oxolane. This is also called tetrahydrofuran. This is called ethylene oxide, because if you take ethylene, that's carbon-carbon double bond, and if you oxidize that, you get ethylene oxide. Okay? Like if you take calcium and oxide, you get calcium oxide, right? The same is true here. If you take ethylene and oxidize it, you get ethylene oxide. That's the name derived from that common process of oxidation. This is oxane. If you have one oxygen, it's called oxane. If you have two oxygens, it's called dioxane. And then when you have two oxygens, you have to start numbering from one oxygen and find out the respective position of the other oxygen. For example, this is 1, 2, 3, 4. 1, 4 dioxane. If I were to have an oxygen here, that would be a big 1, 2, 3. 1, 3 dioxane. So those all kinds of dioxanes are available. Again, these are cyclic ethers. Ethers do not have much chemistry to themselves, but cyclic ethers have some chemistry because of the strain. We'll talk about the chemistry in a bit. These are thio compounds. Same as oxidane, you have thio, so it's called thiene, thietane, thiolane, thiane, and if you have two of them, we call dithiene. And again, the position of that would define where the two sulfurs are. You have only one sulfur, so you call it as thiene. If I were to have another sulfur here, I would call that as 1,3-dithiene. Sulfur compounds are very smelly compounds, unlike oxygen compounds, right? So all those rotten eggs, hair, all the garlic kind of natural products have sulfurs in them. That's the reason why they are smelly. So some of the examples are shown here. If you were to name this as a common way of nomenclature, this would be like butyl ethyl ether. because butyl is one side, ethyl is on the other side, and this is the ether functional group. So ether is the parent functional group in the common nomenclature. But when you write it in IUPAC name, this whole small alkyl group containing oxygen becomes a substituent on the longest alkyl parent chain. So this is butane, and it's at one position, so I don't have to mention that. If I have to mention, I can mention, or even if I say it's ethoxybutane, that's fine. Okay? 1-ethoxybutane is much more official. IUPAC. Okay? And if you have an alkene in the side chain, you have to use geometry of the alkene. If it is cis alkene, you have to mention that it is cis or trans, or E and G. That is that G stands for ethyl, G1 propenyl. That's G1 propenyl. Propenyl only tells you that there are 3 carbon containing alkene. So you have to mention the position of the alkene and the geometry of the alkene. So as you go along in organic chemistry, you need to start using stereochemical descriptions. Just using saying ethyl propenyl ether doesn't cut it. You have to use stereochemical descriptions like E or G, R and S. In this case, for example, when you have chiral centers, for example, this is a transalkene derived epoxide. This is also called epoxide. So alkyl groups, one alkyl group is going downwards, one alkyl group is going upwards. So you got to mention that using trans, E 2-methyl 3-hexene oxide. This is the IUPAC nomenclature of epoxides. These are called epoxides, and this is trans, or you can use E. And the whole thing is regarded as a parent side chain in the common nomenclature. So this is hexane, but the hexane does not give the epoxide. What gives the epoxide is hexene. If you take an alkene and do an MCPBA reaction that you learned in alkenes, right? You learn alkenes in chapter 51. How do you epoxidize alkene? Use a reagent called beta-chlorobenzoic acid, right? MCPBA. And so that trans alkene would have become this epoxide. So it's called 2-methyl 3-hexene oxide. Though there is no hexene as such here, there is no double bond, but this oxide is derived from that alkene. So that's the common nomenclature. So in the IUPAC nomenclature, you got to mention the stereochemistry of the epoxide, and then we use this as a dioxidane, oxidane. It's only one oxidane. So this 3-membered ring is oxidane. Give me 1 minute. So that's regarded as a parent functional group. And now we have 2 alkyl groups on both sides. So this is isopropyl, this is ethyl. So that's put here. Trans 2-ethyl 3-isopropyl oxirane. When you use this as an oxirane parent heterocycle. The other way of naming this is 2-methyl, that is the 2 position. If you start numbering from one end, so that's hexane kind of parent chain, 6 carbons. At 2 position you have a methyl, 2-methyl. That's the geometry of the epoxide, E. And at 3 position and 4 position there are 2 substitutions, right? That is epoxy substitution. So 2-methyl 3,4 epoxy hexane. So 3,4 is the place where oxygen is bridging. That's why you have to mention that the epoxide location has to be mentioned in the IUPAC nomenclature. Okay. So there are various ways of naming these compounds. Yeah.
How is that 2 in the IUPAC? How is it 2 ethyls, 3 ethyls?
This is 2-ethyl. This is methyl.
So what is it?
This is a different way of nomenclature. This you are just using this as an oxidane. That's your parent heterocycle. Let's number them 1 and 2. Okay.
Oh,
Yeah. And then you have other side isopropyl. So that's one nomenclature where you regard 2 positions of oxidane, and then you use the substituents at both the positions. Probably the one that has higher substitution gets the number 1. Isopropyl is a bigger group than ethyl. You got it?
okay. I mean, I just think that, like, if there's only 1 and 2, then why is there 2 and 3 and that? It's just confusing.
It's okay. Let me get it. It's my mistake. Oxygen number 1 in the heterocycle. If you just have the heterocycle itself, that's heterocycle because one of the atom is substituted by oxygen. So that starts with 1, 2, 3. It could go in the other way around also. And then you have 2 substituents at the second position, that's cycle. And the third position is now isopropyl. That's one of the nomenclature. I would take any one of these nomenclatures if you were to write. If I don't test much on nomenclature, so anyhow. Epoxides are very important functional groups in biologically active molecules. Though ethers do not have much of chemistry to themselves, for example, you have diethyl ether. You cannot do any reactions on diethyl ether. Not many reactions can be done on ether. That's the reason why ether is used as a solvent. We use solvent because they don't react with the reactants. Their role is to just mix the reactants, solubilize the reactants, and they don't participate in the reactions. So solvents are normally inert, right? So ethers are good solvents. We use ether in labs, right? You do linear reaction, you use ether as a solvent. You use VHF as a solvent. And then these do not have much of chemistry to it. It's more like an alkane. Just that one of the carbon is substituted with oxygen. Oxygen is nothing much more different than carbon. It does have a little bit of chemistry compared to alkanes, but not that great chemistry. But anyhow, if you were to make this a ring, let's say somehow I converted that into a cyclic epoxide or cyclic substituent. These ethers, for some reason this color is not showing up as well. If I were to have cyclic epoxides, then there will be a lot of chemistry to this compared to the just simple ether, because there is ring strain built into the ring. It's a 3-member ring. To force the 3 atoms into one ring, you need to supply more energy to it. So there is a lot of inbuilt energy in this molecule compared to this molecule. As a result, you have some chemistry for epoxides. Epoxides are strained molecules. They are ready to be opened because they can relieve the strain. Because of the ring strain, they are more reactive. So when you have them in natural products, these centers are normally the centers which react with the enzymes. For example, this is a drug in the clinical trials for cancer. This is called epothelone, developed by some medical center in New York. It's called Sloan Kettering Medical Center. They have this epoxide inbuilt into these molecules. Epothelones are produced by bacteria, and these molecules are active because of the epoxide. They do have alcohols, and these are the centers that fit into the pockets of enzymes, and those are the enzymes that are responsible for cell division. So you have biological activity for these epoxides. So epoxides are a little bit important. Otherwise, ethers are pretty much boring functional groups. There's not much of chemistry for ethers. So let's quickly look into the structure and bonding of ethers. We regarded ethers as derivatives of water, dialkylated derivatives of water. As we notice, there is a deviation in the bond angle because of the bulky groups that we bring in the place of hydrogens. This is alcohol. That's normally typical bond angles in alcohol. But if you try to add one more bulky group here, the bond angles are expanded than what you see in water or alcohols. So nevertheless, this is a tetrahedral shape because you have 2 lone pairs on the oxygen. So they occupy some space, and these groups occupy some space, and there is deviation from the normal sp3 hybridized bond angle. That's something you have to remember. And when you write the ethers in a chemical formula, you would write it as you would write alkane. Zigzag formula is what you would use. Just that you would swap one of the carbons for the oxygen, and that does not change much of the geometry of the alkane. Whatever you learned in Chem 251 is still valid. If this were to be part of a ring, so that's the cyclic ether. still the oxygen is just replacing a carbon. Still this behaves like a cyclohexane in its conformational analysis, and it still has all those boat forms and chain forms that we know. Just that one of the carbon is swapped for an oxygen. However, oxygen has similar structural requirements of carbon because of sp3 hybridization, and as a result there is not much of deviation from the bond angles and the structural features. And how does the physical property get affected because of these bond angles and the structural features? We look into that. We say the alcohols are higher boiling because of the hydrogen bonding. You have a donor of hydrogen. One of the alcohol molecule is acting as a donor of the hydrogen. The other molecule is acting as acceptor of that hydrogen through the lone pair, and they are forming a weak bond that's called hydrogen bonding. And this hydrogen bonding can extend to all the molecules. Extensive hydrogen bonding keeps them in the liquid form. Their boiling points are higher compared to any other molecules, like ethers, for example, do not have the hydrogen bonding. Though we have an acceptor in the form of oxygen that containing lone pairs, but we don't have something that could donate hydrogens. The donors are those which have hydrogens attached to heteroatoms, like oxygen, nitrogen, to some extent maybe sulfur, but or carboxylic acid, right? So this is the donor. The one that can donate the hydrogen to the hydrogen bonding must be attached to a heteroatom. Okay? Though there is alkane has hydrogens, but that hydrogen is not going to participate in the hydrogen bonding. Because that hydrogen bonding is missing, ethers are volatile. Ether, especially diethyl ether, boils at 30 degrees, whereas the same formula containing alcohol boils at 80 degrees or 90 degrees. The difference between the boiling points is because of the hydrogen bonding. That hydrogen bonding has some other roles, especially in the physical states, but they can act as acceptors. If you were to add water or alcohol to ethers, now ethers can act as acceptors, something else will act as donor. So that's the reason why ethers are somewhat miscible with water. They're not completely miscible. Like if you add ethanol and water, you cannot see two layers, right? Because ethanol and water are completely miscible. Whereas if you add ether and water, you don't see one layer, you see two layers. Ether is not quite miscible, but if you analyze the water layer, you would see some ether molecules in water layer because ether can act as acceptor. Ether can act as an acceptor. So if you were to mix these three into water, the more percentage of molecules that you find in water would be alcohol, then ether, then maybe none of the alkane would go into water layer, because this neither can act as a donor of hydrogen bonding nor acceptor of hydrogen bonding, but this can act as an acceptor of hydrogen bonding. This can act as acceptor as well as donor. So the solubility, boiling points, melting points all are affected because of the hydrogen bonding. Normally the hydrogen bonding increases the boiling point. Okay. So they are less dense than water, and that's the reason why we use them as extracting solvents, which forms a top layer when mixed with water, and they are not very reactive, and they are low boiling. If they are low boiling, it's very easy to remove after the reaction. We use ether as a solvent. We use ether as an extracting solvent. Once we do the extraction job, we need to remove the solvent. So the solvent must be low boiling. If it is high boiling, it takes forever to remove. Right? You would put it on the hot plate and you would wait forever and never to get it evaporate. Whereas ether, you can just put it on your bench top and come back next day, it would have gone. Right? So anyhow, so the other cyclic ethers, like THF, that's tetrahydrofuran, that's dioxane. Those are also used as solvents because they are chemically not that reactive. Anyhow, I'm going to skip this slide. So this is about solvents. What type of solvents are they? We talked that there are different kinds of solvents. What type of solvent is it? It has a polar atom. Oxygen is more electronegative than carbon, so the bonds are a little bit polarized towards that, and as a result we have delta positive on one side, delta negative on one side, so there is some dipole creation, and as a result we have some dipole movement. So these are sort of polar solvents, but they are not protic solvents. Polar aprotic is the definition for ether solvents. If you have something like this which has a proton attached to oxygen, you call this as a polar protic solvent. Polar because it has a polar functional group. It's protic because it has a proton that is attached to a heteroatom. But we don't have that proton attached to a heteroatom, so these solvents are regarded as polar aprotic solvent. There are different types of classification of these solvents. You have to look up those definitions. For example, methanol. What type of solvent is it? Methanol has hydrogen attached to oxygen, so it is polar protic solvent. So some reactions demand that you use aprotic solvents, some reactions demand that you use protic solvents. So depending upon the reactions, we choose the solvent. And if you use ethers as solvents, ethers have lone pairs and oxygens, and they solvate cations. Let's say you have ether as a solvent, diether ether as a solvent here, and you use lithium fluoride as a reagent for some reactions, some potassium chloride and sodium chloride. Ethers would line up in such a way that the lone pairs of these oxygens are acting as ligands to the metal. Okay, this is the lithium metal, and they are solvating, like 6 molecules or 5 molecules of ether are surrounding this lithium, and they are solvating, they are stabilizing the lithium cation, but they are not solvating the anion because there is no positive charge in the ether molecule. Anions are stabilized by positive charges on the solvents, cations are stabilized by the negative charges, and as a result you can do the reactions with iodide. Because this lithium is trapped, the iodide is available for if you use lithium iodide. Iodide is available readily for doing reactions. So some solvents help you to do the nucleophilic substitutions than others. This has to act as a nucleophile. Let's say if you use ether, this would trap its counter ion, so this counter ion doesn't bind to this as strongly as it would bind in this molecule, and as a result this is available for doing some reactions. And this is a protic polar solvent. This is just polar solvent, right? This protic polar solvent not only stabilizes the cation but also stabilizes the anion because it has positive center. Hydrogens are delta positive, this is delta negative, so even the fluoride is solvated here. So if I were to do an SN2 reaction, if I use this solvent, the reaction would not go anywhere because my nucleophile is also trapped. Here my nucleophile is free. So depending upon the nature of the reaction that you want to do, you choose your solvents. Ethers are good solvents and they only solvate cations, they don't solvate anions, right? The anions are available for doing reactions. Cations are not available, they are trapped. But you cannot just use iodide because iodide is always coming with some salt, right? Some cation is always associated with it. So you got to trap the cation, you can do the reaction. So what scientists did is, I did some work 10 years back on this research. What scientists did is they connected this R group with this R group and this R group with this R group, and if you connect all these 5 molecules, you have a cyclic ether like this. And this ether is called crown ether because it's in the crown form. All the oxygens are lined up like how your crown would be lined up, right? So this is depending upon the number of atoms in the ring. There are 12 atoms. And there are 4 oxygens, so it's called 12 crown 4. If you have 5 of these units connected to each other, you get 15 crown 5, and if you have 6 of them, you get 18 crown 6. 6 is the number of oxygens. Okay. So now, if you add some salt to it, what would happen? Let's say this is 18 crown 6, right? And if you were to map the electron density of this 18 crown 6, oxygens are the electron dense place, and they have 2 lone pairs. The lone pairs are pointing inwards. So the inside of this ring is electron rich. The outside is mostly carbons, and that is not much of electron rich, right? So if you were to add metal to it, like metal salts, that would be trapped. The potassium would be entrapped between this crown ether. Okay, it's such that this is also called host-guest chemistry. This is called host. This is called guest, and it's tightly bonded. You cannot just extract it away. Even if you use water and wash it, the potassium doesn't come into water. It stays in ether because it's trapped inside. And this kind of extraction is used to clean up the war tanks. If you design a bigger crown ether, you can trap lanthanum or this plutonium, neptunium type of big metals can be trapped, and you can extract them and clean the water tanks. Because these are radioactive metals. Radioactive metals are not good in the environment, so you need to clean them up. So crown ether chemistry is used to clean up the metals, because ethers are good solvating solvents. They are good solvating for the cations. Okay? And depending upon the cavity, you can trap the different size of metals. If I were to trap lithium, I don't need that big a cavity. I can go with 15 crown 5 instead of 18 crown 6, right? Or 12 crown 4 might be good enough for lithium. So depending upon the size of the cavity, you can choose the metal catalyst. In some reactions, we need to use some metal catalysts, but they are not soluble in benzene. Let's say I have to do a reaction in benzene, but I need to use potassium iodide as a part. But I cannot get potassium iodide to dissolve in benzene unless potassium iodide dissolves in benzene. The reaction doesn't work because I need iodine. So what do? I just add a pinch of 18 crown 6, and the moment I add 18 crown 6, all the potassium salt is dissolved in benzene. That's kind of magic, right? So because this solubilizes the potassium by trapping it, now this doesn't look like just potassium. It just looks like as a hydrocarbon species, because all the potassium is entrapped in the cavity, and as a result I can do the reactions. This is called the phase transfer catalysis. You transfer the atoms from one phase to the other phase. For example, if I have to convert this bromide into fluoride, I need to use potassium fluoride, but if I don't use 18 crown 6, this reaction doesn't go. If I just mix the bromo, whatever, this alkyne and potassium fluoride in benzene and go for a month and come back, I would still have a bromide, because potassium fluoride never went into benzene, so the reaction doesn't happen. But if I come back and add a pinch of 18 crown 6, within half an hour this reaction will be over, and that's called phase transfer catalysis. Okay? So what is crown 6 doing? 18 crown 6 is dissolving, trapping potassium, so the fluoride can get into benzene, and fluoride can act as a nucleophile, and the bromide is displaced. So that's the advantage of ethers. That is one of the applications of ether. The second application. The first application is ethers are used as solvents. The second application, crown ethers are used as phase transfer catalysts, metal solvating reagents. Then quickly we look into synthesis of ethers. Synthesis of ethers is normally done from alcohols. So that's the reason why I didn't cover this particular concept in alcohols, because anyhow we would be visiting the very concept in chapter of ethers. So when you have an alcohol, alcohols are electron rich on oxygen, so they can act as a base as well as acid. They can donate this hydrogen and act as an acid, or they can donate a pair of electrons and act as a base. Like water. Water is amphoteric, right? If you have a base, water would act as an acid. If you have an acid, water would act as a base. Same is true with alcohols. So when you have a strong acid, the alcohols act as bases, and they donate a pair of electrons and then accept a proton. The proton accepts as a base, right? So this accepting a proton, this first step is called protonation. Why do we have to protonate it? We'll talk about that in a minute. Anyhow, that's protonation. Protonation is happening on oxygen by taking the hydrogen off whatever the species is. That's acid. It could be water, it could be some concentrated sulfuric acid that you add. Okay. So the first step when you add any acid to any alcohol, that the first step is protonation. So once it protonates, this OH is not a good leaving group, but once it protonates, it's a good leaving group. So it's ready to leave. Anything that can survive on its own is a good leaving group. So that leaves. As a result, it can exist as a water molecule. So as a result, you create a positive charge here. That positive charge is trapped by another molecule of alcohol, and you get this oxonium ion. See, oxygen is donating electrons now to this carbon, so this is called a nucleophile, right? Here we call the same alcohol as a base. So here this is doing a nucleophilic substitution of this, and this is a leaving group, and as a result you get oxonium ion. That is, charge is on oxygen, because oxygen can get 2 bonds, and in this structure it has 3 bonds, so it has to be charged, and you can bring in a neutral molecule and deprotonate. So you got to learn how to protonate, how to deprotonate. These steps are very common in all the mechanisms. We would not be talking about them again and again. I would just say protonation, deprotonation. Right? So when you supply proton to a neutral species, we call that as a protonation. When you remove a proton from a charged species using a neutral species, we call that as a deprotonation. Protonations and deprotonations are very common in organic mechanisms because that's how the catalysis happens. So this is called an acid catalyzed mechanism because acid is triggering the reaction. At the end, that acid is regenerated. So it's not consumed. You use the proton, just shuffle a pair of electrons around, right? So these are called acid catalyzed dehydration of alcohols. As a result, you can make ethers. If you don't add acid, this reaction doesn't happen. So it happens only when you add acid, so you've got to be a mechanism, right? Mechanisms are explanations of reactions. How do they happen? Why do they happen? We just use the powered arrows to explain on the paper. That's what happens in the reaction in one step. All these are intermediate stages, so that there are no parameters, right? You take alcohol and you add acid, and you start heating it for a while. You did this experiment in 263 and 265. You dehydrated some alkanes, some alcohols to alkenes, right? That's also another type of reaction. We'll talk about that. When you take tertiary alcohols or secondary alcohols, elimination is predominant gas substitution. So you get alkenes. If you have primary alcohol, you get ethers, right? That's the reason why we gave you secondary alcohol in the lab to make alkene. But if you were to make ethers, you would take primary alcohols and do an acid catalyzed dehydration. Normally you get some part of alkene form if you have beta eliminations. But if you were to just to substitute, you get ethers. So depending upon the ether that I want, I'll have to choose my alcohol. If I want to make diethyl ether, I take ethanol and add concentrated sulfuric acid, few drops of it, and then reflux it, I get ether. But the disadvantage of this method is that you can only make symmetrical ethers, right? You cannot make asymmetrical ethers because two molecules of alcohols are reacting, so you always make symmetrical ethers. What if I want to make asymmetrical type of ethers? Then I have to go different way. That's the way of synthesizing. That's called Williamson ether synthesis. What Williamson did is he took alcohol and then he added a base. So as a result, alcohols are converted to alkoxides. Alcohol is acting as an acid now. The sodium hydride is acting as a base. This H minus would pick this H, and as a result, you get alkoxide. Any alcohol for that matter. Here we have cyclopentanol, so you get cyclopentoxide. This is the counterion, sodium cyclopentoxide. And then you add alkyl halide, any alkyl halide that you want to substitute. It could be methyl bromide or methyl iodide, and you do a SN2 type of reaction, and as a result you make ethers. These are called mixed ethers because you have two different types of alkyl groups, and this reaction was developed by Williamson. So Williamson ether synthesis would allow you to make substituted ethers. And this is again another reaction of alcohols. So we didn't quite talk about this in alcohol chapter. We are talking here as a method of preparation of ethers. But if you were to discuss this very reaction in alcohols chapter, you would look at this as a property of alcohols. Alcohols upon reaction with bases form alkoxides. Alkoxides are good nucleophiles, so you can do the substitution reactions. So if I have this alkoxide, how do I make this alkoxide? I take pentanol, 1, 2, 3, 4, butanol, and add sodium hydride or sodium. I can make sodium butoxide, and then add alkyl iodide. Here I am adding propyl iodide. So I get butyl, propyl, ether. Okay. There are some limitations to this. As I said, this is an SN2 type of reaction. SN2 types of reactions only work if you have a primary halide as a leading group. If I have a secondary halide or a tertiary halide, these reactions don't go as clean as it works with the primary halide. Why? Whenever you have a secondary halides or tertiary halides, SN2 or SN1 reactions are complicated by elimination reactions. You get E2 and E1. So the best recipe for this reaction is primary halides, right? So That's the limitation of Williamson ether synthesis. It's good for less hindered alkyl halides. You can have sterics on this side because we are not touching this center. We are only touching this oxygen. We are not breaking this carbon-oxygen bond. That carbon-oxygen bond is intact in all the places. So I can afford to have even a tertiary center here, but I cannot have a tertiary center in the nucleophile. Sorry, in the electrophile. This is electrophile. That's the nucleophile. Okay, because this part is responsible for a backside attack, you have to reach to the substituted center, and as a result it's sterically hindered, so this reaction doesn't work. Instead of this nucleophile attacking as a nucleophile, it would act as a base and it would pick up the proton from the next door, because reaching here is much easier. So it takes the proton and this proton goes here and the bromide gets kicked out, and as a result you make alkenes. Got the difference? When you have primary alkyl halides, your alkoxide acts as a nucleophile. If you have secondary or tertiary alkyl halide, your alkoxide works as a base, and as a result you get elimination reaction. So depending upon the conditions, you can tailor the reactions. For example, this reaction works okay because this is the alkyl halide and this is the alkoxide. Though this is sterically hindered, it doesn't matter because this is the one that is attacking here. That makes the ether. But if you were to reverse it the other way around, if you were to take bromide on the side, substituted carbon, and the alkoxide on the other side, your ether doesn't get formed. So you got to choose one as alkoxide and one as alkyl halide. You can reverse it, right? This very synthesis of this ether can be done putting a halide here and sodium methoxide here. You just need one nucleophile and an electrophile. If I snap the loads, still the reaction should work, right? Just that the sterics have to be taken into consideration. Because this is sterically hindered, I would not take this as alkyl halide. I would take that as an alkoxide. See, that's okay because this is what is reaching here. That reaction works and this is fine to go and you get this ether. But the moment I swap it around, I take this as a bromide, that's bulky bromide, and I don't get this substitution reaction. Instead, this acts as a base, picks up the proton, and that becomes alcohol. And these electrons are moved here, and the bromide gets kicked out, and as a result, you make alkene. So, by tailoring the conditions, by tailoring the reactants, you can get what you want. Okay? If you want to make an alkene, you tailor the conditions for an elimination reaction. If you want to make an ether, you tailor the reactions for substitution reaction. Anyhow, there is another way of making ethers that's called silver oxide catalysis of ether formation. This is normally used in carbohydrates. Carbohydrates are polyalcohols, polyhydroxy compounds. There are too many hydroxy groups. Sometimes we need to protect all of them or convert them into ethers. So we use silver oxide and methyl iodide. We can make pentamethyl ether here, right? We will talk about these ethers and alcohols, this type of alcohols. Carbohydrates chapter. We have a chapter for carbohydrates. We'll talk about that. Just to know that silver oxide catalyzes the methylation of alcohols, especially in sugars. And there is another way of making ethers that we learned. In Chem 251, you learned that alkenes can be hydrated, especially when you have asymmetrical alkenes of that kind. If you add water, what do we make? If you have water, you make alcohols, right? You make Markovnikov alcohol or anti-Markovnikov alcohol by doing hydroboration. Instead of using water, if you use methanol, you can do the reaction still. Just that water is acting as a nucleophile here. You are changing the nucleophile to methanol. So instead of getting alcohol, you get ether. So alkenes can be etherified in presence of acid. We talked about this as an addition reaction in Chem 251, where acid catalyzed addition of water would give an alcohol. But wherever you have alcohol, water, you can swap that for alcohol. Depending upon the alcohol I have, I can make ether. If I have ethanol, I can make ethyl ether. If I have propanol, I can make propyl ether, right? So that's one way of making alcohols. The other way of making alcohols is alkoxymercuration. This is oxymercuration. you did oxymercuration in Chem 251 again, where instead of methanol you used water. So you got an alcohol there, right? So instead of using water, if I use methanol, I get methyl group, O-methoxy group. As a result, I can make an ether. So this is called alkoxymercuration, not just oxymercuration. So alkenes can be used to make ethers because alkenes act as nucleophile, and you can catalyze them using acid or mercurium salt, and the mercurium salt is removed at the end using sodium borohydride. This is what is required for oxymercuration, right? So I'm not going to spend much time here. If you were to have an alkene and alcohol in the same group, same molecule, we have a nucleophile as well as an electrophile and the same molecule. As a result, both are nucleophiles. Your mercury is electrophile, so these electrons are given to mercury, and as a result you form a carbocation. Where would the carbocation be more stable? There are two options for this molecule. Let's finish this one before we take. It can form a carbocation here, or it can form a carbocation at this tertiary center. Which one? So this is also a tertiary center here, but there is one carbon missing between both of them. I'll put that carbon here. So this is Hg. So out of these two centers, one of them is more substituted. The more substituted gets the positive charge. That's more stabilized positive charge because that's a tertiary carbocation, and we have a nucleophile within the molecule that would reach across here, and as a result it can make a cyclic ether. Right? That oxygen is donating the electrons to the carbocation, and at the end we do the sodium borohydride that removes the mercury, we get the hydrogen. So you can make different types of ethers using all these reactions. In the next class we'll talk about the reactions of ethers.